Log on, tune in, find out. Another good idea from Cambridge.
Verificatum.
Yes, thank you. So first of all, I have to agree completely with you. I think we should go ahead on with the people that are implementing things. And I will explain why. So first of all, who am I? I did my PhD, and I focus on mixed nets, and this is one way of doing electronic elections. So I started with electronic elections already in 2000, and this was before there were efficient proofs of shuffles. So we actually.
You agree
Oh.
to use it.
Do I need this?
If you need to.
Is it on? Can you hear me? Okay. Yeah, so I'm basically raised to do complexity-based cryptography with proofs, okay? And I started writing this code as a hobby. Actually, it started to verify a paper that I wrote, to verify that the formulas was correct. And then it gradually became more serious, and now it's fairly serious. Okay, so let's start with mixed nets. So there are different voting systems out there, but one particular type of voting system consists basically of three parts. You have some scheme for identifying eligible voters, and you have a scheme for producing ciphertext, encryptions of the ballot, of the vote, and then you have some scheme for tabulating, okay? And the tabulating scheme could be, there are basically two schemes, homomorphic tabulation and mixed-net tabulation, and this talk is about mixed-net tabulation, okay? So that's the context. So what is a mixed-net? We have a bunch of senders, and we have a mixed-net, and the simplest way to view a mixed-net is like this. Each sender submits an input, and then we get the outputs, but in sorted order or some canonical order, random order, okay? This doesn't really fit well into the voting schemes, so what we need to do to make this fit in a nicer way is to view it like this instead. The mixed-net produces a public key. The senders encrypt their votes and send them to the mixed-net, and the mixed-net decrypts and sorts or randomly permutes the output, right? So again, this is a trusted party in this model. So in some sense, this is the best you can hope for a mixed-net. A trusted party that outputs a public key, gets those ciphertexts and outputs them in random order. Okay, so there are some small technicalities here. The crypto system needs some kind of non-malleability property, and you need to weed out the duplicates and so on. But basically, this is the idea. Okay, so now let me say something about provable security. And I've talked with some people here during this workshop, and this might be a little bit controversial. Okay, so I'm asking, is this paranoia? Okay, I claim that a moderately complex protocol, and now I'm not talking about the two-party protocol even, maybe a multi-party protocol. If this is constructed by a nobody, then it's almost surely insecure. Okay. If it's constructed by a system security expert, it's almost surely not secure. Okay? If it's constructed by a cryptographer without the proof of security, it's pretty likely not secure. It's you have a lot of experience, but the minute you step outside the confinement of your well-known schemes, you're basically on enemy territory, in my opinion. Okay, so the next thing you could consider is a cryptographer that produces a scheme along with a proof, but there could be bugs in the proofs, of course. So who reads the proofs? And the mod could be unrealistic. So this is the best we can hope for. A cryptographer produces a scheme with a proof in some standard model that we basically understand, and the proof is verified by multiple cryptographers. So that's the best we can do. And then we have to implement it. And I think many people here knows a lot more than I do about implementation. So if you look at my scheme, please report what you find. Okay. So let me now try to motivate my point of view. This is the history of heuristically secure mixed nets. Okay? You have a scheme by Park, Ito, and Kurosawa. It was broken a year later. You have a scheme by Jacobson. It was broken 2 years later. Another scheme by Jacobson, also broken. Another scheme, also by Jacobson, by a chance. It was broken, I broke it. There's another scheme, broken. And very recently, we looked at the scheme that was proposed by a company called Untitled. Untitled is a company that are selling voting schemes. So they run an election in Norway. So we can't break that particular setup because they basically have 2 trusted servers. So it's not really, it's not so easy to say what it means to break it. But they have a paper where they present their vision of having this run in a multi-party setting. And this scheme we have reported, we're corresponding with them currently to, to try to convince them that they should do this in another way. So, if you consider what the previous speaker, I don't remember your name, sorry, said, I mean, some of these attacks are theoretical attacks in the sense that you might be able to change a few votes, or you might be able to break the anonymity of somebody by corrupting a lot of parties, right? Some of these attacks are really, really bad, right? So this attack, you can replace everything and break the anonymity of everybody, right? This last attack is not so bad, actually. But you can break anonymity of a particular voter by corrupting, say, 100 voters. So you can choose the celebrity votes and recover what they vote for. And then recently, we broke another scheme. This is a more famous scheme. This is something that is actually implemented by other researchers. And basically, we thought it was secure. That was our starting point. We wanted to prove this secure by adding a few things. And then it turned out that a small little detail renders it completely insecure. You can replace the complete output without detection. So I'm not going to say anything like that. But I think this is pretty interesting. That, like, this is the protocol that was considered secure by the voting community at large, but nobody bothered to do the little details. And if you look at one of these details, it turns out to be like really bad. I still think that this is a really nice basic idea, and we still think that we can prove it secure if you add a few things, right? So I'm not saying that the basic idea is completely wrong. Okay, so that's the history. What about provably secure mixed nets? Based on proofs of shuffles, like Jens told us about. Well, so far as I know, there were only a few minor bugs. But then again, this is based on an old paradigm. You construct a scheme which is private, and then you take out your big zero knowledge proof hammer and make everybody prove that what they're doing is correct, right? So this we understand pretty well. And this is what I've been trying to implement. And so there are previous attempts. There are some based on heuristically secure ones. Like we're corresponding currently with the people that implemented this RPC stuff because it's really bad. And typically they don't have any threshold robustness. So if one mixer loses their keys or everything breaks down, somebody does something really bad, there will be no output. So this is not really practical, I think. And also, this is my theory side talking. I think it would be cool with a protocol which is really provably secure. No random oracles, nothing. Just to show what happens. And also, they're using patented proofs of shuffle, so it's unclear how you can use it. And the code is not open source or free. Like there is an implementation done at NEC by Katsu Sacco and Jun Furukawa. Okay. Yeah, so maybe I should say this as well. Like there are several ways of verifying the execution. So in my scheme, this is completely distributed. In previous schemes, you typically have a central verifier. This is the case in next scheme, for example. Okay, so my implementation is based exclusively on provably secure protocols, and I'm trying really hard to be faithful to cryptographic theory. So for example, when I'm using a CCA to secure crypto system, I really have a labeled crypto system where tags are globally unique for the particular protocol instance, so you cannot move things around in the protocol and stuff like that. And it's fully distributed, and I hope that there are no patented protocols, but I'm probably wrong about this. I'm not a lawyer. Yeah, and it's open and free. Go ahead and try it and so on. Okay, so what is implemented? So this is for those of you who really know this stuff, this is not going to be any news. Okay, so we start with a homomorphic crypto system like El-Gamal, and the nice property about this is that the message group, the randomness group, and the messages, the randomness, and the ciphertext, they are all groups, and you have this nice homomorphic property that if you multiply two ciphertexts, you get a new ciphertext where you have basically multiplied the messages and added the randomness. So yeah, there's nothing, I mean, the multiplication here and the addition here, those are group operations. They could be the same, but not necessarily, typically not. Okay, so a very cool property of this is that you can take a ciphertext, U, and you can multiply it by a ciphertext of 1, and this means that you have re-randomized it. So you get a new ciphertext which is identically distributed to the original one, but independently distributed. So that's a very nice property, and this is used in mixed nets. Okay. So what is a re-encryption mixed net? It is this algorithm, and now I'm going to use at least some of those many square meters of blackboard that we have. So a mixed net, you have, sorry about that. Okay. I'm really trying now. Actually, I'm going to do this. Okay. Okay, so you start with some list of ciphertexts here. The first mix server re-encrypts and permutes them, and this gives us a new list. And you continue like that until you have a very last list, and then you do something called joint decryption. I will explain all of this part. I'm going to use this notation. Okay, and here T is the number of mix servers that you will involve in this mixing process. And this is, as you can see, we have K mix servers, but only T of those are going to be involved, and this is because we are going to use a threshold scheme. So now I'm going to add something here at the top. So what does it mean to jointly generate a public key? We're going to do this such that it's verifiably T threshold secret shared. By this I mean that you need T pieces, T shares to recover the secret key. Okay. And then there is no point in shuffling more than that many times, right? And the second thing we need to do, we need to define what this L0 is. That's a list of ciphertext where each party encrypts something like that, but then they also have to make this non-malleable, right? And remove duplicates. So we make this extractable, so it could be CCA to secure or with a proof of knowledge. There are several ways of doing this. Okay. And then we need to fill in some details here. So what does it mean? Well, each mix server picks some randomness and a random permutation, and they compute a new list, their output list, by taking each ciphertext, re-encrypting it, and permuting the whole thing, and defining that as the output, right? And then they also have to prove that they did that correctly. And if they did that correctly, we continue. And, oops, there's a slight typo here, it should be T. We finally decrypt this list LT and output the resulting plaintext. And then the question is, what do we do if this zero-knowledge proof is wrong? Well, then we simply take the previous list, and I'll define that that's the output. So remember, this is a multi-party protocol, right? So if I'm one of the other parties, I'm simply going to verify this proof. If it fails, I'm going to take the previous output and expect the next mixer to start with that output instead. Okay. Another thing that we need here, which is a really cool protocol, I think, is an idea by Feldman that was then generalized somewhat by Pedersen. So you have a bunch of parties, and you have a threshold T, and the goal here is for the dealer to share a secret in a verifiable way. So in a verifiable way means that the other parties, when they get their shares, they can verify that their shares are okay. So they know that they can recover the secret. Okay, so the dealer, he gets some input, A, 0, and then he picks some other input randomly, and then he publishes some checking elements. Okay, so I'm going to make a picture here, I think. No, apparently not. So you have the dealer. Okay. Okay. He generates some shares, and he's going to do this as follows. He computes the share as follows. So note that this is really an evaluation of a Shamir secret sharing protocol. And then, each party checks their own share by doing this. And if you note what happens here with these alphas is that actually this is an evaluation of this polynomial in the exponent. So this really should hold if the share is correct. So this is where you have this verifiable property. Then this dealer, if somebody complains, then he publishes the share, right? So this way, a receiver cannot falsely accuse the dealer to give bad shares. Okay? And if somebody discovers that any complaint was wrong, then we can set this, we can say we can abort. But in practice, when you code this, it's much more convenient to say that you set this to some trivial value where everybody knows their shares, like that 1 share or so. Okay, so that's the way it's implemented. And finally, if you want to recover A0s later, this is a secret sharing scheme. So from the shares, you should be able to recover the secret. You simply publish your shares. You identify some other valid shares using this test, and then you Lagrange interpolate. Okay. So this protocol is cool because you can use it in several different ways to solve the problems, to solve these issues that to implement the things that we need in the protocol, right? So first of all, we can use it to do this distributed key generation. So what does each party do? He picks a random secret. He executes Feldman verifiable secret sharing. And then we let this be the first checking element of ESS, right? So this is going to be this alpha 0. That's G to the secret. And we define the joint public key as this product. And note that this allows key parties to recover each individual secret key, right? Feldman verifiable secret sharing is not really a secret sharing scheme because the secret is not hidden, right? You reveal G to your secret. So from an information theoretical point of view, there is no secret at all, right? But computationally, it is very nice for settings like this. Okay. The other thing we need is distributed decryption. So recall that we compute Y such that it is the product of all the individual public keys. So this means that we have this property, right? And then to decrypt a ciphertext, each party simply publishes this decryption value. They compute this using their secret key, and they get this decryption value. And to make sure that decryption is performed correctly, they prove that they did this correctly. So now you see that it's the same xj here, and this is xj is determined by the public key. So if you prove this, you know that the decryption was done correctly. And then you simply piece together all of them, and you get this, and you decrypt, right? So that's the first thing we can use this for. Then we also need a proof of a shuffle, and Jens explained one proof of a shuffle, and this is my own with my student proof of a shuffle. Actually, this is the goal of this paper was not to do a proof of a shuffle, but it was like a side result. Okay, so I hope that everybody will be able to follow this, because I think it's a very, very simple proof of a shuffle. Okay, so the goal is to prove that some output list was really the result of re-encrypting and permuting an input list. Okay? So this means that you should have this property for some permutation and some R. And here it might be a bit, it's actually pretty convenient to permute also the randomness, to keep them together. Right? Then you can view this as you re-encrypt and then you permute the result. Okay, so here is an idea. We have a matrix, and eventually the prover is going to commit to this matrix and claim that it is a permutation matrix. But at this point, we simply have a matrix. Okay? And then we can define an n-degree polynomial, Fm, over this ring, which is basically the product of the rows of, the components of this vector, right? So you simply evaluate, you take these variables and you evaluate on the matrix. You get some linear, linear functions, and then you take the product of those, right? You can do that for any matrix. Okay, like this, if you want to write it down. The inner product of each row. Okay, and now the nice thing is that M is a permutation matrix if and only if this holds. This follows from unique factorization, and you can also, like, the easy thing to see is that if there are two elements that are non-zero in any column, you will get a square in there, right? That's easy to see. The other thing is if you have two non-zero elements in one of the rows, you get something which is a linear expression involving more than one variable. Right? And so this test actually shows that you have a matrix which has exactly one non-zero element in each row and in each column. And this test then forces the matrix, forces each non-zero element to actually be 1. Okay, so that's the idea, and then we apply an old idea from, I think this is from property testing. So if you have a polynomial which is non-zero polynomial and you simply evaluate it, it's pretty unlikely that you're going to hit 0, right? So we can test this. We can define our own polynomial as this difference, and then we can test if the matrix was a permutation matrix or not by simply evaluating that polynomial. Right? So now if we can commit to a matrix and do this test under commitment, using homomorphic properties, then we're in good shape. We can prove that the committed matrix is a permutation matrix. And that's exactly what we're going to do. So we're going to use a homomorphic commitment, which is very much like those that Jens talked about. But for the purpose of this slide, you only need to know that it has a nice homomorphic property that allows you to take a commitment, evaluate the matrix on the commitment, and get a new list of commitments, which are really these linear expressions. Okay, and then you apply standard techniques to prove that those EI primes are actually that they have the same product, and you also prove this, which is even simpler. Right? So that's the whole idea for doing this. And then we have this ciphertext, right? If you remember, our original goal was to prove something about these ciphertexts. Who cares about the matrix, right? But the point is, if we now have done this, then we can simply append this to our proof. We let the prover also prove that if those EI primes are used, then he knows additionally R such that this relation holds. So note that EI, those are chosen by the verifier, right? So he picks those randomly. And the prover has to prove that all these properties hold, and this means that the matrix is a permutation matrix, and this means that if the matrix is a permutation matrix, then those EI primes are actually a permutation of the original EIs.
How many verifiers do you have?
This is one, honest verifier, public coin verifier.
But in your protocol,
Yes,
who are the verifiers?
the other parties.
And you do one proof for each one of the verifiers?
No, they do it jointly. I'll get to that.
They choose the randomness jointly?
There are two ways it's implemented. So, right, either you follow the righteous path of provable security, which is not secure in practice probably, but then you do it using coin flipping. And again, we have this nice Pedersen VSS. So now I'm cheating a little bit here, right? Because before we used Feldman VSS, and this is the only thing I described. For Pedersen VSS, you basically do the same thing, but instead of committing to a single secret like that, you commit to something like this, where this is your secret, and this is some randomness. So this hides your secret perfectly, but now you have a binding property under a computational assumption, the discrete log, right? So I'm cheating here because we don't have this H value yet. Where do we get the H from? H, yep. Okay, so the idea here is simple. You commit to your secret, the secret coin. Everybody commits to the secret coins. Actually, they secret share it, right? And then you recover it, all of those coins, and you take the XOR basically, but in this field. Or you use a random oracle to flip coins, and coins are all you need to run this proof of shuffle, and actually also to run the distributed decryption. Right? But we need this H. But nicely, we have this Feldman VSS, right? We can use this again to generate a common element of the group, which, it's independent. It's hard to compute the discrete log of this element in our standard basis G. So note that there's no real need for this to be perfectly random or random looking even. All we need is that if you break the discrete log of this in our basis G, then you can break the discrete. We need some kind of reduction, and there are papers about this. I'm not going to go into this. Okay, we also need a bunch of independent generators, because if you remember from Jens' slides, he had stuff like this. I don't know. C1, right? stuff like this where you commit to several things using different generators, and you blind it with this. So, you know, this matrix commitment is actually a bunch of those. So we need those independent generators. But now we can do this. We simply pick some random WIs. Each party does this, and then it proves knowledge of all those exponents, and then you combine it all to get your generators. And this might seem like a very convoluted way of doing it. Why not simply output your generators randomly and commit to them or whatnot? But this is what you have to do to make the proof go through, actually. So if you want to, you know, walk the righteous path, then you have to do that, or you can use a random oracle, right? And this, I think this is a nice, like a bootstrapping procedure. You generate one generator, and now we can run Pedersen. And if we run Pedersen multiple times, we can flip coins. And coins allows us to very efficiently generate multiple of those generators. And then using those generators, we can execute an efficient proof of a shuffle. And we can, of course, use the random oracle instead to generate those random generators. Okay. So in the code, I've actually implemented this in two ways, but under a common, common shell. So there's like a challenge piece of the code that is doing the challenges, and depending on how you configure it, it will compute those random oracle proofs, or it will do actually this, this stuff. Okay. So what is good about interactive proofs? It's because it's the righteous path. But then you can say, well, that's very nice, but under what assumptions are your random coins random? Maybe it's okay to trust the decision diffie-Hellman assumption for hiding something, but I might feel a bit wary of trusting the correctness of the whole election under this assumption, right? And actually, when you do this distributed these secret sharing schemes, how do you distribute your secrets? Well, you're probably going to encrypt them using some crypto system, and one provably secure scheme is Kramer-Schupf. That's probably the most efficient one. And this is only secure under the DDH, right? So, a practitioner, a very conservative person could say, well, I don't really like that. And then also, if you want people to be able to verify the correctness of the election after the fact, then all these servers have to be willing to execute, a one-to-one zero knowledge proof with an outside auditor, like a newspaper or whatever, right? And it's not really nice to keep those secrets lying around. So the advantage of fiat chemie is that, yeah, it's cryptographic, theoretically unsound, but it seems to work. And we can destroy the secrets, which is really nice in practice, I think. This is a very important, this is perhaps more important than the practicality issue of not being online and so on. That, I think, can be solved. But I would like to see an insanely conservative standard hash function. This would be a good thing to have, I think, for applications like this, where you want the security to be really, really high. Okay. We also need this bulletin board. I think I can use a little.
Of course, you started about 10 minutes late.
Okay. Good. Yeah, so we need a bulletin board, and this is one component of this implementation that is not really done. It is done, in a good way in the sense that it's provably secure, but it's bad in the sense that it's not robust. So all the rest of the code is threshold and everything is neat and tidy, but this part is really simplistic. If I want to publish something, I put it on my web server, which is a very stringent, conservative web server, you could say. But I put it there, and I put my signature on this message along with this unique label I get from having a hierarchical scheme of subprotocols and instances of subprotocols. So whenever I publish something, it's published under a unique label. I sign the label along with a message, and then everybody else will sign that and put their signatures online. And if I can fetch all the signatures, then I'm happy. This is a published message. right? So there are several things that can go wrong in the sense that the protocol can halt. Right? If somebody simply doesn't publish a signature, the protocol will halt. So this is something to deal with in future work. Then in terms of primitives, I have wrappers of standard stuff. So all of this is written in Java and C, and this is basically wrappers of standard stuff. And then we implemented provably secure primitives to walk the righteous path. That's part of the project. So we have Merkel-Damgaard and Kramer-Schupf signatures and so on. Yeah, so this is, maybe I don't have to say much about this. And groups, there are two types of groups. We have the modular groups and we have the elliptic curve groups. And they are implemented on two levels. So either you can run pure Java code or you can run C code with native calls to the C code. So it's fairly fast. One thing that is quite different, I think, from other implementations is that I don't have any implementation of Al-Gamal. There is no such thing as Al-Gamal. There are only group elements. And Al-Gamal is really a pair of group elements, right? But we can view this as an element of the product group. This is really glorified lists, if you like. But it's very neat to implement it like that, because then your code becomes simpler. Like Feldman and Pedersen, those are very similar protocols. You can generalize it to any collision-resistant homomorphism. And this sounds really fancy, but it's just a way of saying, well, we can implement in such a way that we can run parallel instances of this protocol, or we can run Pedersen or Feldman with the same piece of code. And also you can shuffle multiple ciphertexts in parallel. So if you want to implement preferential voting schemes, then you need to somehow shuffle a bunch of ciphertexts together so that they stick together, and then you count something on the part of it, you decrypt part of it, and then you want to shuffle that again. So if you have multiple, if you have a ranked election where you rank your candidates, you encrypt all your candidates, then you can implement this easily on top of this code. Okay. And then representing objects, this is something that I have debated with a lot of people. I decided to not have anything from standards. No DRE, no ANS, whatever. It's a very brute force simplistic approach. If you have an integer, you encode it as an integer in 2's complement. If you have a field element, you do the same thing, but for a fixed size of your byte array. And groups are represented in the same way. And if you have structured, like sometimes in a protocol you want to submit several group elements, or maybe one group element and a list of group elements and so on. This is all implemented in a way that meshes correctly with these product groups and so on. So if you implement your own independent verifier of the whole thing, you can either implement it like I do with these rings and whatnot, or you can do it naively and just look at these lists of elements as lists of elements instead of as elements from a product group. So I think this is a good choice. We have a bunch of optimizations. So first of all, I'm using pre-computation at the protocol level. So parts of this execution can be pre-computed. Batch proofs are used for the decryption. For those of you who know this stuff, I'm just, it's just information. It's not really fixed base exponentiation. This speeds up. If you want to compute g to the xi for many xi's, you can do this much faster than simply computing each one naively. Simultaneous exponentiation is the same thing. Exponent slicing and everything is threaded. All the heavy computing is threaded on multiple cores. But all of this is except this, I guess. All of this is hidden as far down as possible in the code, right? So this stuff, You don't see that in any logic code. It's done inside, encapsulated in small pieces. So there are very few loops higher up in the code, which I think is important. And then you can ask how fast it is, and I discussed this a little bit with Steffi. I think that the numbers that Jens and Steffi gave were not entirely accurate. I off a little bit for the number of exponentiations. But the main point here is not that. The main point is that it's really difficult to compare things fairly, because if you want to compute something like this, right, then you need to take into account how big is this x, right? So if you're using a prime order modulus, which is of the following form, which is nice if you want to embed messages in this group, then your normal x will be pretty big, right? They will be 2000 bits. But some of those exponents that appear in the proofs or shuffles are smaller. They're like 200 bits. So if you're using such a group, you shouldn't really count those as complete exponentiations, right? Whereas if you're using an elliptic curve group or a small subgroup, like the one that Jens and Steffi considered, then it's really there are no small exponents really, right? Unless you use a really huge elliptic curve. So that's one thing that can be, change the stuff. And then how do you count pre-computation? If you have a protocol where if you do pre-computation, it's faster in the online phase, but if you combine the two, the cost of two, the cost of both, then, so there are many things like that you can consider. And I think the fair way to do this is, you set up some parameters and you try it. So in that sense, I think, what Jens and Steffi did was fair. For those parameters, that's what you get. Okay, so the status of documentation is that the code is structured and commented. There are detailed installation instructions and so on. And the code, I think the main two things that are complete components that are missing is the bulletin board. This is the main thing. And this is really difficult to do actually, because it's not only a matter of having a trusted bulletin board. It's a matter of how long do you wait for a message before you decide that there was no message. And you cannot have a trusted party doing this, because then that party can actually kick out players from the protocol. So this means that you will trust that party completely, which is not acceptable. So it's not okay to have like a semi-trusted bulletin board that only is allowed, that doesn't work. If you want to prove the security, it doesn't work. You need something which is distributed. And then of course, killing bugs. I wrote most of this software myself, and I am not a professional programmer. I did my best, but I'm sure that plenty of you are much better. So if you have a look and you see something really weird, please let me know, and I will try to fix it. And that's it. Okay.
Time for one or two quick questions, perhaps?
Yes?
Can you give us an idea of how close the structure of the code is to the structure of the verify model? Is it,
I'm sorry, how close?
How close the verify model and the implementation in Java are? Is it really line to line, or is it different structure?
Something that I did hide here is that I have this technique for cutting the proof for shuffle in two. Like you do pre-computation where you do this matrix stuff, and then you do something much faster for doing the actual proof when you prove stuff about the ciphertext. So you can do a lot of computation before you even see any ciphertext. But apart from that, the logic is basically this. But I mean, any code, you have to care about, checking the formats of stuff. When you start reading something that comes on your network, you need to worry about, recursive depth if you're doing a parsing. I mean, there are lots of small details that you have to worry about. And I think I worry about some of them, but I'm sure that there are things that are, if you spent your life on software engineering, there are certain things.
Yeah, so my follow-up question is, did you use any tools to automatically check these kind of things?
No.
Or do you do everything by hand?
you're welcome to help. Yeah.
Okay.
Okay.
Oh, Jens has a question or comment?
Yes.
Sure. If I understand correctly, then
Yes.
you have actually had this in use in a voting protocol. Could you say some words about that?
Yes, I should say it was used by Wombat. It's a voting project. Wombat, and maybe you haven't heard of it. It's some people at Tel Aviv University and IDC Herzliya in Tel Aviv as well. So they used it. I will go there right after this workshop, and they will use it again, I guess. And I'm also cooperating with the trustworthy election system. No, trustworthy people know the
Voting
name. Your
systems.
project. What's the name of the project? TVS?
The Luxembourg one is Certus, but
Yeah. Okay.
TVS in Surrey,
Yeah.
Surrey, Birmingham.
Yeah. So I'm cooperating with other people because, like I said, this is not a complete voting system. It's one component, and I'm trying to do that component well, and hopefully other people will use it.
So it may get rolled out in the Victoria Electoral Commission in Australia with provably with
Yeah. Possibly. Yeah.
Verificatum back in.
Yeah.
We hope. It's ongoing.
There is more information on the homepage about, other more details. So. Yes.
I think actually we should probably stop
Okay.
because already
Yes.
10 minutes
Sure.
behind lunch.
Sorry.
Douglas, you'll be here over lunch, so people
Yes.
want
Feel
to
free
interact with you.
to.
Just before we thank Douglas, let me make a couple of administrative announcements.